We'll start our discussion of conservation of mass with first defining what we mean by mass flow rate. So what we're looking at here is, if you think about mass flow, okay, you have a small area that the mass is flowing through, right? If you got some sort of fluid flow, okay? So the V here is the velocity, and delta T is time. So if you think about the definition of mass, or what we call mass, a density. If I have the density of a fluid, density is mass per volume. So if I take, to get mass, it's density times volume, where the volume is defined as the small area that the flow is going through times basically the height of this cylinder, this column. Okay, and if we think about perpendicular flow or normal flow, we take that velocity normal to that area times delta T, which is the change in time. That gives us a distance, which is essentially area times the height. That gives us the volume that we're looking at. Okay, taking that volume times the density will give us the mass. Now, moving delta T over with mass, we get what's called mass flow, right? dt, right? And then we have rho times the normal velocity times the area that which it passes through. Okay, so this is what we call our mass flow. Again, mass flow is going to be the time rate of change of mass, right? So it's dm dt. Okay, now if we look at one-dimensional flow, which is what we're going to be looking at, like flow through pipes and things of that nature in thermodynamics. Okay, again, the flow is going to be normal, perpendicular to that boundary. Okay, and the properties are basically uniform across the area. Okay, that's what we're calling one-dimensional flow. So from that, then basically I no longer have dA. It's just that fixed area of the pipe that it's flowing through. Okay, and I get rho times that area times the velocity. Basically, I drop my integral. Okay, and now again, we don't like to talk about things in terms of rho. We'd rather talk about specific volume, which is the inverse of rho. So you get the area times the velocity over the specific volume. That's the equation we mainly use for mass flow. Now, capital A, capital V, again, that's area times velocity. That's our volumetric flow. And a lot of times we've heard about that maybe in CFM or cubic feet per minute, or maybe cubic meters per second. Something like that is what we call our volumetric flow. But that relates basically this volumetric flow, specific volume, and our mass flow from that equation there. Okay. Now, as far as conservation of mass concerns, again, what we're looking at here is a control volume. Okay, so flow is coming in and out, and here I have one inlet, one exit. We could have, several in, several out, that sort of thing. Okay, so if I think about the control volume here, basically the dashed, what I'm calling my system here. Okay, the change in mass as a function of time of this is basically what's coming in. Okay, and the mass flow of what's going out. Okay, so that is the conservation of mass principle, basically. What's coming in minus what's going out, that's what's going on. Now, for the problems that we talk about here, okay, we're talking about steady state. So there's no change in the properties. Properties, once you get up to steady state, okay, basically the change in mass, there's no change in mass as a function of time within that. That goes to zero, and basically what you get, and this is our conservation of mass principle, is the mass flow in equals the mass flow exiting. Okay, and that's for steady state, which is the types of problems we deal with here in thermodynamics.